This program is brought to you by Stanford University.
All right, let's review a little bit the basic equations of cosmology, and then I want to take you through a little tour of these equations and what they say about the structure of the universe. And then perhaps we will get to the subject of dark matter. I want to talk about dark matter a little bit also because most of the matter in the universe is dark. So I will discuss that with you, and I will explain to you in what way it is either mysterious or not mysterious, depending on your taste. All right, we derived the Friedman, Robertson, Walker, Lemaitre, I don't know who else, equation from energy conservation, assuming that the universe was homogeneous. Incidentally, in this course, I never show these beautiful pictures of galaxies and everything else, just because I don't know how to run the projector up there, among other things. But I will draw for you the universe the way it would look in one of these gorgeous, gorgeous pictures. You just have to substitute black for white and white for black, and then it looks like this. It somehow looks better when you invert the color. And on a scale larger than the size of clusters of galaxies, there are clusters of galaxies. On scales larger than sizes of clusters of galaxies, millions of light, many millions of light years. Many, many millions of light years, but not billions of light years. Smaller than billions of light years, bigger than millions of light years. The universe looks pretty homogeneous, pretty smooth. Okay, so assuming that it's good and smooth, and concentrating on one galaxy, doesn't really have to be a galaxy. It could just be an imaginary particle moving along with the flow, and thinking of ourselves as the center. There's nothing important about where we are, but just to get an orientation, thinking of ourselves as the center of coordinates. We studied the equations of energy conservation for this particle, thought of as a Newtonian particle moving under the influence of gravity, the gravity due to everything within a sphere centered on us and with radius equal to the distance of the sphere. I'm just going to go through that again because it's really simple. If we choose, let's put the galaxy over here on the x-axis, and in fact let's put it at x equals 1. If it's at x equals 1, that means its distance. Okay, what is its distance then from us? If it's at, and we are, of course, x equals 0. Its distance is then, by definition, the scale factor a. That's the definition of the scale factor, the distance at x equals 1. The distance at x equals 2 is 2a, and so forth and so on. So we could concentrate just on this galaxy by itself, that's that coordinate x equals 1, and we can study how it moves under the influence of everything else in there. It has an energy. Its energy is, first of all, a kinetic energy of outward motion. Its kinetic energy of outward motion is 1/2. Now, its velocity squared, its mass. Let's also let its mass be 1. Let's let its mass be 1 unit. Then I don't have to keep writing masses, which just cancel anyway. 1/2 its mass times its velocity squared. And what is its velocity squared? If its distance is a, then its velocity squared is just a dot squared, where dot means time derivative. That's its kinetic energy. What about its potential energy? Its potential energy is minus the mass contained within here. Now, what's the mass contained within here? It's 4 pi over 3 times That's the volume of the sphere. No, that's not the volume of the sphere yet. We have to multiply it by a cubed. That's the volume of the sphere. We multiply that by the mass density, and that's the mass of everything inside this shell. 4/3 pi, that's volume, times a cubed, times the density. Okay, that's the mass in there. But remember, the gravitational potential energy is the mass times g divided by the distance. Let's call it just distance. So we have to put g in there, the potential energy, and then divide by the distance, and the distance is just a. What does Newton tell us? Newton tells us that this is constant and independent of time. So this is just some constant, and I called that constant, I think I called that constant minus k. And making it minus k does not necessarily mean that it's negative. K can either be positive or negative, but I just called it k. And that is the basic equation of cosmology. To make it a little bit more familiar, I don't know, familiar or not familiar, depending on your background. First of all, we can divide by a and make this a squared here. Now we can divide the entire equation by a squared. Let's first multiply by 2. Let's first multiply by 2 to get rid of the half here. That makes this 8 pi over 3. And I should have called this thing k only after multiplying by 2. The standard notation would have this being minus k after I multiplied by 2. But in any case, it's constant, so it doesn't matter whether I call it k or 2k. Now I divide it by a squared, and I get a dot over a squared. That's the square of the Hubble constant, or the Hubble non-constant. Let's shift this over to the right-hand side, and that becomes 8 pi over 3 g, and I've divided by a squared, so this a squared is no longer here, times the mass density, and then minus k divided by a squared. The a squared, I just divided both sides of the equation by a squared, and this is the Friedmann-Robertson-Walker equation. Friedmann, FRWL, and everybody else. I'll tell you now, although it'll take us till next week. Next week we will discuss it in a little more detail, the connection with Einstein's equations. I'll just remind you that the Einstein equations, in particular the time-time component of the Einstein equations, have the form of some tensor which is composed out of the curvature tensor. What is it? It's r 0, 0 minus 1/2 g0, 0 times the curvature scalar is equal to what? Is equal to t naught naught with a constant in there, which is related to, there's also some 8 pi's and 3's. There's also some, I can't remember the exact numbers, but I think it has 8 pi over 3 and g in it. But things of that nature. All right. The connection is simple with this equation. If I transpose all the things without any energy density in them, a dot over a squared plus k over a squared, that's the left-hand side of Einstein's equations. If we plug in an expanding metric, which we'll write down in greater detail next time, if we plug it in and calculate the left-hand side, guess what we get? We get a dot over a squared plus k over a squared. On the right-hand side, we just get the energy density. Rho is, of course, the mass density, but mass and energy are the same thing, E equals mc squared. And so this equation really is nothing but the time-time component of the Einstein equation. I tell you that now just for orientation's sake, that we have not abandoned Albert for Isaac. But at this stage, Isaac and Albert say the same thing. So we might as well think about Newtonian mechanics to get a first orientation. All right, now, next thing we did is we plugged in, or we assumed a form for rho, for the mass density. And I'll tell you from now on, I'm going to call it the energy density. Okay. The energy of a system at rest. Now, why are we talking about a system at rest? Because our coordinates are moving with the material. So the material in the coordinate frame that we're using is everywhere is at rest relative to the coordinates. And under those circumstances, rho is nothing but the mass density at rest, or the energy density at rest. All right, so let's take a little cube. We take a cube, which is one coordinate unit on a side. That means its length, width, and height are a, the scale factor itself, okay, and prescribe how much mass is in there. Let's assume there is a mass m in there. There's some value of mass in there. And furthermore, under the assumption of homogeneity on a large enough scale, every cube of the same size has the same mass. So let's just call it the mass m inside that cube. Then what is the density? The density is m, which is constant. The energy in that cube, it stays constant. The masses move, but they don't go into or out of the box. And so the amount of mass in there stays constant, but the mass density is m divided by the volume, which is a cubed, and that's rho. So now we can write our FRW equation as a dot over a squared, Hubble constant squared, is equal to 8 pi g over 3. And now m, this constant m, divided by a cubed. This is not the mass of any specific object. It's just the mass within this cube. I call it m. Maybe I should have used another letter for it, but it doesn't matter. The mass in the unit cube minus k over a squared. All right, we decided last time, and I'm going to continue for the time being, not imagining, but using the empirical fact. It is an empirical fact, an observational fact, that this constant k is very close to 0. It's too close to 0 to tell whether it's positive or negative. I will tell you now, it does correspond to the curvature of space, but it's too small to be able to tell whether it's positive or negative, and it's a very good approximation in cosmology just to ignore it. And that's the simple equation which describes the expansion of the universe. This is called the matter-dominated universe. It's matter-dominated. What that means is that this formula here corresponds to a situation where you have the energy in this box just in the form of particles at rest. You count up all the masses in that box. If the masses were moving with a tremendous velocity, there would also be kinetic energy, huge amounts of kinetic energy in the box. And then we might say that we were talking about, and if the kinetic energy was bigger than mc squared, or bigger than just m if we set the speed of light equal to 1, that means that the particles are moving with very close to the speed of light, then we would no longer say it was matter-dominated. When one speaks about matter-dominated, one is speaking about the mass distribution being made up of things which are essentially at rest, moving with the flow. So in that case, yeah.
Apply the temperature.
for the time being, since we can think of these as particles, and the particles are not moving, we can, for the moment, just say the temperature is 0. And we can also say the pressure is 0. If all the particles came to rest in this room, if the room got so cold that all the particles came to rest in the room relative to the coordinates of the room, there would be no pressure. Pressure happens when there are particles crossing the boundaries of this box. And we will see, it is important. We're going to come back to it. But matter-dominated means the particles are at rest in the box, moving together with the box as the box flows along with the flow of galaxies. Then, under those circumstances, those are the circumstances, we should label this now matter-dominated. There may be other forms of energy around, so there may be other contributions, but in our universe today, well, I was going to say something false. I was going to say our universe is matter-dominated. It is actually not. It is dominated by dark energy, but we'll come to that in a little while. But all of the ordinary matter, galaxies, protons, neutrons, they all add up. And this is the so-called matter-dominated universe. The last time we solved the equations not by solving the equations, but by guessing an answer. Standard honorable method to solve equations. We said, let's try a power law. You might have tried something else. You might have tried sine or cosine or hyperbolic Nugi function or whatever. But first thing you always try is A is a power law. So we tried constant times time to a power, and we plugged it in. What do we find? We found, first of all, to match the two sides, we had to choose P equal to 2/3. Maybe I should go through that again very quickly. If this is A dot is Cp t to the p minus 1, and A dot over A is equal to, the C's cancel out, and we just get P over T. Square it, and we get P squared over T squared. So the point is, the left-hand side is proportional to 1 over time squared. The right-hand side is proportional to 1 over time to the 3p. A cubed goes like t to the 3p. So we have to have t to the 3p being t squared. That means that p has no choice but to be 2/3. So that tells us that the universe expands as the 2/3 power of the time. It doesn't expand linearly. A doesn't grow like time. It grows like the 2/3 power of the time. And we can also plug in, and once we know that, then we can plug back into the equation and compute C if we like. C doesn't tell us very much. It's just if you're doing the bookkeeping and you want to keep track of everything, you want to keep track of everything. And if you do, you find that C cubed is equal to 6 pi mg. You work it out. This is the more interesting thing here, that the universe expands as the 2/3 power of time. What does that look like if we were to plot it? If we plot vertically the scale factor, horizontally time, then the 2/3 power looks, I don't know, something like this. Linear would just be a straight line. This is not as strong as linear, so it turns over like that. Okay, that's the matter-dominated universe, and it was the way the universe behaved for a rather long time. It behaved this way from about 100,000 years in age. That's pretty young. The universe is 10 billion years old. From about 100,000 years in age to about a couple of billion years, a billion or 2 billion years or something like that, it behaved according to this matter-dominated law. Now, before that, the universe's energy was dominated by something else. It was dominated by radiation, not by matter. So let me explain why. The universe today is filled with photons. We detect those photons. Most of the photons are in the microwave range. For the moment, we're not going to discuss where they came from. They are the remnants of the Big Bang. But let's just take it as an observed fact that there are a large number of photons floating around in the microwave range. And in fact, roughly, there are about 10 to the 9th photons for every atom or for every proton in the universe. So the universe, in terms of numbers, just in terms of population, is largely made of photons. On the other hand, the photons have very much less energy than the protons, or even the electrons. The protons have energy mc squared. The photons have no mass, but they do have energy. They do have energy. Every photon has energy, but let's talk about that energy a little bit. Incidentally, when one speaks about the photon having an energy mc squared, we're talking about the rest energy. How do we get away with saying the photon has no mass, but it has an energy? Well, we're not talking about the rest energy of the photon. The photon has energy, but it's moving. If you tried to slow it down to rest, it would just disappear and would have nothing, no mass, no nothing. So photons have energy, and let's discuss the photons. Why, in the very early universe, the universe was radiation dominated. That means dominated by the energy density was mostly in the form of photons. Why that's true? So let's begin with the formula for the energy of a photon. Again, we can think of a box, a unit on a side. It's filled up with photons. Now photons move. That means photons can pass out through the box. But on the average, there are as many photons coming into the box as out of the box. And so the number of photons pretty much stays constant in the box. But unlike the protons, the energy of a photon depends on the size of the box. So let's discuss that a little bit. Let's begin with the energy of a photon. The energy of a photon. Standard symbol for a photon is a gamma. That doesn't mean it's a gamma ray. Gamma rays are just high energy photons, but gamma is the standard symbol for a photon. The energy of a photon is equal to Planck's constant, this terribly tiny constant, 10 to the minus 30 or whatever it is, times what? Times the frequency of the light that that photon is composing. Let's call that nu. What are the units of nu?
1 over time. 1 over time.
Yes. But there's yes, certainly. Hertz. Cycles per second. Cycles per second. This is also h bar omega, but I'll just call it h nu. Now, we have a wave going by us. We are necessarily, because we've already studied quantum mechanics and we're completely familiar with quantum mechanics, completely comfortable with it, we have no trouble jumping back and forth from wave to particle picture, right? Good, okay. So, associated with these photons is a wave. And the wave moves with the speed of light c. And if it was just an ordinary wave in this room moving past us with the speed of light, it would have a wavelength lambda. A wavelength lambda. And the shorter the wavelength, clearly the bigger C, stand there with your nose watching watching the wave. You're watching the wave go past you, and the electric field goes up and down and up and down and up and down, and it oscillates. It oscillates with a frequency. That frequency is nu. It's quite clear the faster the speed of light is, the larger the frequency, the more cycles per second, and the shorter the wavelength, the larger the frequency. So the frequency is equal to the speed of light divided by the wavelength. So we can rewrite the photon energy as h times c over lambda. The important thing here is the lambda in the denominator. Now, what happens to a photon of a given wavelength as the universe expands? And here is where we will make an assumption. The assumption is very well justified by studying the dynamics of electromagnetic waves. But here is the assumption that as the universe expands, the photon wavelengths expand with it. Okay. Imagine, for example, a wave in a waveguide or in a box. And that wave is the longest wavelength that you can have in that box. It looks like that. It has no nodes. In other words, it doesn't oscillate, just has 1/2 of an oscillation. What happens as the box grows? As the box grows, the wavelength expands to match the box. It will not jump to a wave with a node in, or with nodes in. Nodes mean places where it goes to 0. It won't do that. It'll just expand with the box. As the universe expands, it's like an expanding box, and the wavelength of every photon gets stretched in proportion to the increased factor of the scale factor. In other words, the wavelength, whatever the wavelength was, if the scale factor doubles, then the wavelength doubles. The wavelength is proportional to the scale factor. Okay. Another way to say it, well, no, that's good enough. That's good enough. Every photon has a wavelength that is not frozen in time, but grows linearly together with the scale factor. That means, since the wavelength is in the denominator and the wavelength is growing with the scale factor, it means that the energy of the photons is decreasing as the scale factor grows. And in particular, the energy of any photon, whatever its initial energy was, it will scale like some constant divided by the scale factor. As the scale factor increases, the wavelength gets longer, the energy decreases. So we have this box of photons now. There's a given number of photons in the box on the average. It's true they pass in and pass out of the box, but on the average there's a given number of photons in the box. Every single photon, as the box expands, its energy scales like 1/A. Now, that means that the total amount of energy in this box won't be a constant like m, as it was when we just had non-relativistic stationary particles there, but it will scale like a constant divided by A. Now, m here does not mean mass. It's just a label. It's just a parameter. Whatever the energy in the box, as A expands, the energy will decrease like a constant divided by A. That's the energy per photon. Now, how many photons are in the box? Let's suppose that there are in photons Sorry, I made a mistake. Let's just call this something over A. Constant over A. That's per photon. But if every photon in the box has an energy that goes like 1 over A, and the number of photons stays fixed, that means the total energy in that box also scales like 1 over A. That's the point. So the energy in this box, energy in the box, is some constant divided by A. Now, what's the energy density in the box? The energy density in the box, you take the energy and divide it by the volume of the box. So we divide by the volume, and the volume is A cubed. So that's another A cubed in the denominator. And what we discover, here's the discovery, that the energy of a box of photons, as you expand the box, goes like 1 over A to the 4th power instead of 1 over A cubed. When all we had was particles at rest, we said the total mass in the box was m. We divided by the volume, and we said the mass density was m over A cubed. But for photons, because each photon's energy decreases as you expand the box, it's 1 divided by A to the 4th. Okay, so let's go back now. Now imagine that the universe, instead of being filled with protons, neutrons, electrons, ordinary particles moving slowly, let's imagine that the universe is filled with photons. As I said, photons pass through the box, they come in and they go out, but we'll assume that the number of photons in the box on the average, as many come in as go out. In that case, we have to modify the equation. Which equation? This one over here. We have to modify it, and instead of the right-hand side being m over A cubed, it now becomes m divided by A to the 4th. So this is now the radiation-dominated universe. It looks pretty similar. A dot over A squared equals, same thing, 8 pi g over 3. And now the energy density, which instead of being m over A cubed is a constant, which I called m again, different constant, divided by A to the 4th. It even has different units now. Well, can we solve that equation? Yeah, we can solve that equation. We do it the same way. Let's plug in, let's make a trial solution. A equals C t to the p. Again, A dot over A is just P divided by T. That's A dot over A. P divided by T. We square it. P squared over T squared. That's the left side. Now let's go to the right side. 8 pi g over 3, m, and now A to the 4th. So now I'm going to have in the denominator C to the 4th. That's not going to be very interesting, but T to the 4p. A to the 4th is C to the 4th times T to the 4p. And now, if I'm going to match both sides, this one goes like 1 over T squared as time goes on. This one goes like 1 over T to the 4p. 4p had better equal 2. Otherwise, they can't match. Okay? So 4p had better equal 2, or p equals 1/2. So we've discovered that the radiation-dominated universe expands not like T to the 2/3, but like T to the 1/2. Square root of t, in other words. This and we can also calculate the constant c. I'll leave it to you to calculate the constant c. It's not very interesting. Oh, well, I'll tell you what it is. C to the fourth is 32 pi over 3 times gm. That was not very illuminating to me either. But the fact that the universe expands like t to the 1/2 power instead of t to the 2/3 is somewhat interesting. Okay. Yeah.
Why is there a G in there?
There's always a G in.
G is normally gravitational. Right?
This is the gravitating effect of energy. Remember, in Newton's theory, okay, good. It's a good question. We discussed it last time, but let me come back to it. Not last time, last quarter. Newton's theory is the theory of things moving very slowly compared to the speed of light. The dominant form of energy when things move with slow compared to the speed of light is just the mass, the mc² energy. You may think of m as being simply the energy plus a little bit of kinetic energy may be there. All right. When things move near the speed of light, then the energy is not proportional to the mass. It's more complicated. For example, photons, which have no mass, do have energy. But the right-hand side, or the thing which gravitates, the thing which pulls, the thing which causes gravity, is not rest mass, it is energy. When the object is slow, then its energy and its mass are the same. A rapidly moving photon will gravitate, will cause things to be pulled toward it. Another example, here's an example. Take a box and fill it with lots and lots of radiation. Radiation, so much radiation that it would melt the walls of the box, but let's make walls that won't get melted in our imagination. And we fill this box with a huge amount of radiation. That box will gravitate more than the box without the radiation in it. It will have more energy. E, if the box is at rest, its energy is the mass times, and it will gravitate. It will gravitate and pull things toward it. So it's energy, which is the thing which gravitates. When we're writing this equation here, this doesn't really stand for mass, rest mass. It stands for energy density. Okay? So it's energy density which gravitates, and it gravitates proportional to Newton's constant G. Okay. Yeah.
Is either of these equations solvable with an a that decreases with time?
Oh, yeah. In fact, I mean, if you put back the 1 over a squared, the k over a squared term, you'll find examples where it increases and then decreases. Or maybe we'll do that. For the time being, it's not too important because there's no, I mean, it may be important conceptually for some reasons, but the universe does not appear to be doing anything like that. Yeah.
But the equation it is a solution to the equation.
Yeah.
What happens to the energy? You said the energy per photon, so the total energy goes down. What happened to conservation of energy?
No. These equations are conservation of energy. This is kinetic energy. Let's put back the k and multiply by a squared. These equations state conservation of energy, but there's two kinds of energy. One of them are the ordinary things such as photons and protons and neutrons and everything. They go on the right-hand side. The left-hand side is the energy of expansion. It's the energy of the gravitational field. It's the thing which is left out until you know about general relativity. Okay? So these are, well, actually, what is it? It's really the kinetic energy of the outward moving things. Here's kinetic energy. Here's the energy of the object in a frame of reference in which it's at rest. So in other words, this is the rest energy of a box moving with the flow, and this is its kinetic energy. It's the sum of them which is conserved. And if you set it equal to 0, in other words, if you set this minus this equal to 0, that's surely conserved. So it's a balance between two kinds of energy, kinetic and potential.
Just that assertion about it's the energy that's doing the gravitating,
It's the other kinds of energy, yeah.
that is not clear until you go to general relativity. I mean,
That's right. That's correct. Right. You might have guessed it from special relativity. E equals mc squared. You might have guessed it. In fact, Einstein did guess it. That's exactly how he guessed it. What he did was he first examined, he studied a box of photons like this. And he said, what's the mass of that box of photons? All right, so here was his thought experiment. He said, let's push on that box of photons. When you push on the box of photons, just take the box by itself. It takes a certain force to accelerate the box because the box has a mass. But now when you start to accelerate the box, more photons hit this side of the box than hit that side of the box because you're pushing the box. This wall is moving away from the photons, this wall is moving toward the photons, and so you actually have to push a little bit harder to push against the pressure, the radiation pressure in the box. That means effectively the mass of the box is a little bit bigger. And Einstein worked it out, and he found that the extra mass, the extra inertia of the box was in fact proportional to the energy of the photons in there. That was the origin of E equals mc squared. Now, he also had rather early the idea of the equivalence principle, that gravity works the same on all objects. And from that, he came to the conclusion that the Earth would pull on this box as if it had a mass not equal to just the mass of the original box, but the mass plus the photons in there. But if the Earth pulls on the box pulls on the Earth, et cetera, et cetera. So rather early, he had the idea that energy gravitates. Okay. Took him a while to get it all together. And ultimately, yes, it's the general theory of relativity, which tells us that, that it's energy which goes on this side. Right. Remember last quarter we talked about having to make tensor equations, and the left-hand side of Einstein's equation is a tensor. The right-hand side is the energy-momentum tensor, composed out of energy and momentum. Okay, so we have two kinds of cosmologies. Real cosmology is a combination of both of them. But let's try to understand under what circumstances and when and at what times the universe might be matter-dominated and when it might be radiation-dominated. In fact, it is a question of when, whether the universe is matter-dominated or radiation-dominated. The reason is the following. I just explained to you that as the universe expands, the energy density of radiation decreases. But it follows that when the universe, if you imagine contracting it, going backward, the energy density of radiation must have been much larger. If you squeeze it, it's larger. If you let it, all right. So at some point, when the universe was really squeezed, where the wavelengths of all the photons were really small, the photons had more energy than the ordinary matter. Yeah.
So, as the universe ages, does the P go continuously from 1/2 to 2/3?
Yeah.
So
Not abruptly, for sure, but you know, more or less in a fairly narrow range of time. It doesn't jump. I was going to say it jumps. It doesn't jump. It goes continuously from 1/2 to 2/3.
But there's a space where it gets very steep and then
Well, I was about to draw, give you a rough idea, but let's just plot just to get the idea up on the blackboard. All right. Let's first plot energy density, E density. And let's draw both cases. The matter dominated, here's the matter dominated. It looks the matter energy density. And that goes, it goes to 0. I'm It does go to 0. And how does it go to 0? It goes to 0 like 1 over a cubed. It also becomes infinite when a goes to 0. This is, let's see, this could be, yeah, this is a. A on the horizontal axis, scale factor. When the scale factor goes to 0, that's the situation where the universe is shrunk to a point, the density becomes infinite. All right. Now this is the matter energy density. Let's write matter out here. And then there's radiation. The radiation is 1 over 8 to the 4th. 1 over 8 to the 4th is smaller when A is big, but bigger when A is small. So 1 over 8 to the 4th looks like this. And at some point, they cross. Right? At some point, the matter density becomes less than the radiation density. So sufficiently early, if we go back far enough, the universe was radiation dominated. Okay? What does that mean in terms of exactly what was asked before? What does that mean about the growth of the universe? It means it started out early. We'll try to estimate in a moment where this happens, when that happened, in a little while. All right. If I plot, now I plot something different. I plot the scale factor versus time. Okay. The scale factor versus time. Here was energy versus the scale factor. Here's the scale factor versus time. The scale factor for radiation dominated goes like the square root of time, t to the 1/2. And that looks like this. And let's extrapolate it. Okay. But at some point where this crossover happens, it's a bad approximation beyond that to say that the universe is mainly radiation, the energy. It becomes mainly matter. At that point, and it's not a sharp point. There's a region in here. It makes a transition from t to the 1/2, from square root of t, to t to the 2/3. T to the 2/3 is bigger than t to the 1/2. And so that's what the universe looked like for a fairly long amount of time. The interesting question is, where did that point happen? Okay, so we can talk about that a little bit now. Oh, no, before we talk about that, let's talk about temperature. Let's talk about temperature. I want to talk about the various interesting things which happened. One of the things which happened was this transition from radiation dominated to matter dominated. That happened after about 10,000 years, roughly speaking. Something like about 10,000, maybe a little more than 10,000 years. 10,000 years after the Big Bang. Okay. Something else happened, which is actually observationally more dramatic. What happened to the photons if you run the universe backward to early times? If you run it forward, their wavelength grows. If you run it backward, their wavelength shrinks. What happens to the energy of the photon as you run it backward? Increases. What does that mean about the temperature of the universe? It goes up. It goes up. In fact, to a good approximation, the temperature of a black body, or the temperature of a box of radiation, is basically just the energy of a single photon. It differs by some numerical factor. So apart from some trivial numerical factor, the temperature of the radiation, this is the temperature of the photons which are moving around through the universe. They have a temperature, and their temperature changes with time It goes like 1 over A. Now when I say it goes as 1 over A, I just mean it's proportional to 1 over A. If A doubles, the temperature becomes half as big. If A quadruples, the temperature is 1/4 as big, and so forth. So the bigger A, the smaller the temperature, the smaller A, the bigger the temperature, and just proportional to 1 over A. Okay, now, that means as we trace backward, there was a time when the temperature was much hotter. In fact, there was a time when the temperature was as hot as the surface of the sun. The surface of the sun is rather different visually than the space around it. In particular, the sun is opaque. You cannot see this. It's not because the sun is too bright to see the stars behind it. That's not why you can't see the stars behind it. You can't see the stars behind it because the starlight hits the sun, hits the material of the sun and gets absorbed into the sun and gets rattled around and just gets absorbed by the sun rather than transmitted through the sun. The sun is opaque. Why is it opaque? It's opaque because it's ionized. Ionized means that the atoms have been separated into positive and negative charges. An ordinary atom is electrically neutral. Because an ordinary atom is electrically neutral, it means that an electric field doesn't accelerate it. A vibrating electric field doesn't do much to the atom. It may cause the atom to change size and shape a little bit, but it doesn't accelerate the atom because the atom is neutral. But if the atom were replaced by a proton and an electron, let's say a hydrogen atom, if the atom was replaced by an electron and a proton, freely moving, not bound to each other, the electric field would slosh the electrons back and forth. It wouldn't slosh the protons as much because the protons are heavier. So when an electric field passes through an ionized material, it sloshes the electric charge back and forth. And when it sloshes the electric charge back and forth, the electric charge behaves as an electric conductor, and electric conductors are opaque. It's the reason that a mirror is opaque. Why can't light go through a mirror? Why does it bounce off? Because the light hitting the mirror drives electric currents, and the electric currents radiate the signal back. So an ionized material is very opaque. If you heat up hydrogen, and in fact we haven't discussed it very much yet, what was the universe made out of? What is the universe made out of? Mostly hydrogen. Universe is largely hydrogen. It was even more hydrogen in the past. Hydrogen and some helium. But if you go back early enough, the temperature was high enough that the helium and hydrogen were ionized. The electrons were pulled off the atoms, and it was opaque. It was hot and opaque. In fact, it was about like the surface of the sun. Okay? Let's ask when that happened. See if we can figure out when that happened. Well, there's a particular temperature. What's the temperature of the photons today? 3 degrees. Today's temperature today is very cold, 3 degrees absolute zero, above absolute zero. Okay? What is the temperature near the surface of the sun? Anybody know? 3,000 degrees, something like that. 3,000 degrees, about 1,000 times larger. About 1,000 times larger. So the temperature at which the gas ionizes, let's call that the ionizing temperature. And it's also more or less the surface of the sun. That's about 3,000 degrees. Well, if the temperature varies like 1 over A, as A gets smaller and smaller, the temperature goes up, that means that at the time of ionization, the universe must have been, the scale factor must have been 1,000 times smaller than it is today. The temperature scales together with the scale factor as 1 over A. If the temperature today is 1,000 times colder than it was at ionization, that means the universe must be 1,000 times bigger. Let's see if we can figure out when that was, at what time that was. Let's define a time. Let's remember the following now. The scale factor grows like t to the 2/3 today. T to the 2/3 during the matter-dominated era. The late times were matter-dominated after the universe cooled down a bit. All right? So A grows as 2/3. What this tells us is that the time to the 2/3 today divided by the time at which ionization happened to the 2/3 must be about a factor of 1,000. The scale factor today is 1,000 times bigger than it was at ionization. The scale factor is proportional to the t to the 2/3. And so this tells us that the scale factor today to the 2/3 power divided by the scale factor at ionization to the 2/3 power must be about 1,000. All right, we know what the time today is. What's the time today? This is today.
13.7. 13 something.
About 13.5 billion years. It's about 13 point, that we measure by measuring the Hubble constant. That tells us how fast the galaxies are moving apart. If we run it backwards, it tells us how long it was since the galaxies were sitting on top of each other. 13.5 billion years. Let's call it 10 billion years. This is 10 billion, so this is 10 to the 10th to the 2/3. Well, let's see. What shall we do? If we take if we take the 3/2 power of both sides, it becomes t today divided by t at ionization is equal to 1,000 to the 3/2. I've taken the 3/2 side of both equations. The 3/2 side of something to the 2/3, they just cancel out. What's 1,000 to the 3/2? What's the square root of 1,000 is about 30? So that's about 30,000, right? Yes? It's 30,000, isn't it? Yeah. Yeah, it's it's 1,000 to the 1 plus 1/2. 1,000 to the 1 is 1,000. 1,000 to the 1/2 is 30. 30,000. Okay, so that's 30,000. 3 times 10 to the 4th in years. No, sorry, it's not in years. 3 times 10 to the 4th. Okay, so that tells us that T ionization, let's just solve that for T ionization. T ion, the time when ionization happened, if we run it backwards, is equal to T today. That is 10 billion years. 10 to the 10th divided by 3 times 10 to the 4th, right? Did I do it right?
Should use 13 and a half at the top.
13 and a half.
A billion.
Would
Instead
you
of
like me
10
to
to the
put
10.
13 and a half on point 3?
Are you rounding it down to 10
I was
billion?
doing order of magnitude.
Okay.
so-
Yeah.
Okay.
13 is 10.
Okay.
13 is 10. Well, we can adjust it later. All right, so 10 to the 10th divided by 10 to the 4th is 10 to the 6th. This is 10 to the 6th. That's 10 to the 5th times 10 divided by 3. 10 divided by 3 is 3. So that's 300,000 years. After 300,000 years, before 300,000 years, the universe was completely ionized. It was completely opaque. Light could not travel very far. It was a dense plasma of torn apart atoms. The nuclei were mostly hydrogen with a bit of helium. And the main thing is it was hot and opaque, as hot as the sun, as the surface of the sun, and opaque like the sun. Now let's think about what that means to an astronomer. It's an astronomer with a very good telescope. Here's the astronomer at the center of the universe, and the astronomer looks out. And as he looks out, he looks into the past. All right, so if he looks to the next galaxy, the Andromeda, he's looking about 2 million years into the past. That's not much. If he looks out to some distant galaxy out here, he's looking further into the past. And the shells are both distance as well as time. Backward in time as you go further and further out. Well, as you go further and further out, the temperature of the photons is increasing. The temperature locally out here to a traveler who is traveling with them is higher than over here because he's looking back into the past. And as you look back into the past, the temperature was higher. Eventually, at some distance, namely about 13.5 billion light years, he sees back to the point where the universe is ionized. So, and out beyond that, the universe is completely ionized, and light cannot penetrate it. It just scatters around. Light just scatters around in here. And then, at some point as you move in, it becomes cool enough for atoms to recombine, and become unionized, for the electrons to get trapped by the protons and form atomic hydrogen and atomic helium. At that point, the universe becomes pretty transparent. Why is it transparent? Because it's not a plasma anymore. So way out far, it's a plasma. Out to some place, no, of course it's a fuzzy place, it's not a sharp place. It's a fuzzy place where the universe goes from being a plasma to being or a time at which the universe went from being a plasma to being a clear system with just some neutral atoms. At that point, light can travel through the universe without scattering very much. This surface, where you go from plasma to ordinary gas, is called the surface of last scattering. That's the surface of last scattering. A photon rattling around there will come to that surface of last scattering and then pretty much be able to freely move through the universe. So when we look out, all the things that we normally see are on the inside of the surface of last scattering. And we can't really look out beyond the surface of last scattering, not with electromagnetic waves anyway. Yeah?
So okay, so basically what you're saying is our limitations with our telescopes, radio, etc., they cannot look beyond 300,000 years ago.
That's it, yeah. Not 300,000 years ago, but they can't look back, right, earlier than 300,000. Now, are there other things that can look back? Yes. Neutrinos are electrically uncharged. They don't get scattered by the ions in there. Neutrinos just pass through an ionized gas. Eventually, it gets hot enough that even neutrinos interact with each other strongly. So there's some other shell out here. It's the surface of last scattering for neutrinos. But with a neutrino telescope, which doesn't exist, of course, such a thing doesn't exist, but with a neutrino telescope, if you could see the very low energy neutrinos, then you would be able to see deeper into the past. A graviton telescope could see even deeper into the past. But why, when we look out in the sky and we look up here, don't we see the surface of the sun in every direction? This is a modern form of Olber's paradox. If it's true that out here everything is as hot as the surface of the sun, why don't we look out at the night sky and see the bright glare? Redshift. This is not standing still relative to us. It is moving away from us with very close to the speed of light. And that means that every photon on its way in here has been redshifted by a factor of 1,000. That's what made the temperature go from 3,000 degrees to 3 degrees. So what we look out and we see is microwaves of temperature 3 degrees. That's not much of a signal, a 3-degree black body. You don't see it. 3,000 degrees, if you looked out in every direction, you'd burn your eyeballs. So
For neutrinos, is that when neutrons separate into protons? And
Wait, say it
electrons?
again.
A moment of last scattering for neutrinos, when the neutrons and electrons, excuse me, protons and electrons?
No, I think it was earlier than that. It was at the time when the weak interaction was as strong as the electromagnetic interaction, which was a good deal more energetic. Yeah, I don't think that's, no. And, right, and the gravitons even further back, but they're even harder to see. And what makes them hard to see is the same thing which allows them to get through this junk. The reason they get through the junk is because they're so weakly interacting.
So you can see that sphere. That's what you see in the cosmic background radiation.
You see this sphere.
Right.
I'm talking about the neutrino
No, I
sphere.
mean that surface. We do in fact see that.
Oh,
surface.
yes. Yes, that is what you see when you see the cosmic microwave background, absolutely. Yeah.
Didn't gravitons go all the way to the beginning?
What is that?
Big Bang. Gravitons. Why would there be a shell for gravitons? What would be opaque to gravitons?
Oh, gravitons become strongly interacting with each other when the energy gets high enough and when the temperature gets high enough.
And what would be the distance from the Big Bang to that point?
The Planck distance. The Planck distance, 10 to the minus 33 centimeters. Right, 10 to the minus 42 seconds. So, well, the point that I was raising, though, was it's the same thing which makes them be able to get through this junk, which makes them hard to detect. They're hard to detect because everything is transparent to them, including the detectors. Right. Yeah.
So if I understood correctly, the surface of the sun is where it seems to be because that's the temperature at which light becomes opaque to light. So that's why the sun is the size it appears to be.
That's the temperature at which the ionization, which it's called recombination, where the atoms recombine. Now, why is it as sharp as it is? The sun has a fairly sharp edge when you look at it. And the answer happens to be the exponential behavior of the Boltzmann distribution. I didn't want to get into that today, but
on that same subject, when you talk about the temperature of a photon, you're talking about the temperature of a black body whose peak radiation is that temperature.
Yeah.
Is that correct?
Yeah.
But that is not linear in label.
the temperature is essentially the energy of the average photon. Okay? The average energy, the photon has an energy which is 1 over its wavelength. So yes, the temperature is 1 over the wavelength of the radiation. No. That's energy density. That's not the energy of a single photon. T to the 4th is either the energy density or the energy flux, the luminosity. Yeah. T to the 4th is a combination of the energy per photon and the number of photons per unit volume. Okay? So in order to find the energy density of a black body, you have to know the energy per photon and the number of photons per unit volume. The number of photons per unit volume goes like T cubed, and the energy of a photon goes as T, and that's what gives you T to the 4th altogether. Yeah. Yeah.
How about the neutrinos don't have any intrinsic motion? I mean,
They move with very close to the speed of light.
the photons, you can't stop them, so they're always going. But aren't the neutrinos that aren't they sort of just go to, if you had a box full of neutrinos, doesn't that same, why are they moving? Our matter is not moving relative to the boxes that are growing with the rate of the universe.
Photons move, yes?
The photons move.
Right,
I'm talking
but-
about neutrinos.
Hmm?
I'm talking about neutrinos.
Why do neutrinos move? Well, the first approximation, they're massless, so they're very much like photons. They have a teeny, 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 tiny mass.
So they have to. So they're very high. So you can't treat them.
Their energy is much larger than their mass.
You can't treat them like
As
like
non-relative.
nanoparticles. They have to be treated separately.
For practical purposes, you can treat them as being like photons. Yeah. Yeah. A neutrino would have to have a very, very, very low energy in order for it to be moving much slower than the speed of light. So, it's only recently, it's only in the last several years that people have really been able to measure the mass of the neutrino because it's so small. And for all practical purposes, not all practical purposes, but for many practical purposes, neutrinos just move with the speed of light.
So these original neutrinos also are very cold in some sense or another.
No, they were hot.
They were hot, but
Yeah.
now
Now they're probably about a little bit colder than the photons, maybe 2 degrees. But similar to the photons.
Do you know what time after the Big Bang the scattering for neutrinos?
I would have to say, but it's microscopically small. It's much smaller. Yeah. Yeah. And we'd have to do some work.
Is that why it's 2 degrees cooler? Because that surface is farther out?
Well, the surface is no. It's cooler. Yeah, it decoupled earlier, and yeah. And then stuff happened that was out of equilibrium and heated the photons. It didn't heat the neutrinos. So, nobody, of course, has ever measured the neutrinos. People, I believe, estimate something like 2 degrees, but it will be a little bit colder. Yeah.
and how about dark matter? Would that also?
Okay, now we want to talk about dark matter. Now, let's talk about dark matter. All right. All right, dark matter was not discovered by studying cosmology, where cosmology means the universe as a whole. Cosmology means the study of things bigger than a few billion light years. Anything smaller than that is astronomy. And then they've invented this word. If it's ugly astronomy, ugly, difficult astronomy, meaning to say that it's not neat and elegant, then they call it gastronomy. That's not my word. Yeah. All right, so the dark matter, which certainly has an important cosmological consequence, very important, but it was not discovered by cosmologists looking at cosmology. It was discovered by astronomers looking at galaxies. And so a galaxy is a small object on the scale of the whole universe. And measuring what are called the rotation curves of the galaxy. The rotation curves are simply the rate at which things move around, the orbital velocity of stars at different distances from the center. So let's start with orbital velocity, and let's go all the ways back to the solar system just to get a handle on orbital velocities. The solar system, or any system which is composed of a central mass and an orbiting, one or more orbiting planets, let's call them. All right. Now, what I'm interested in, the mass of the central object is m. The things orbiting around it are considered to be lighter. And I want to know the velocity of an orbiting object as a function of its radius, as a function of its distance from the center. The orbiting object, let's say the orbiting object has a mass little m. Okay. All right, let's see if we can work it out. What we use is Newton's equations, F equals ma. What is the, and we're applying it to the planet. All right. What is the force on the planet? The force is due to the sun at the center. It doesn't have to be the sun, just some central object in some orbiting planetary system. The force is mg divided by r squared, right? Where r is the radius of the orbit. That's the force, and it's directed radially inward. That's equal to the mass times the acceleration. So we have to know is the acceleration of an object moving in a circular orbit. I'm going to write down the answer. The acceleration of a circular orbit is toward the center. It involves the velocity and the radius. Anybody know the formula? V squared over r. I am not going to prove that. We're just going to check its dimensions. What's the dimensions of acceleration? Dimensions of acceleration are length per unit time per unit time. Length per unit time squared. Velocity per unit time is acceleration. Velocity is length over time per unit time. Let's just check that velocity squared over r has the same units. Velocity squared has length squared over time squared, and r has length. So hopefully these have the same units. They do. Okay. It's a true fact that the acceleration of a circular orbit is toward the center, same direction as the force, and it's proportional to the velocity equal to the velocity squared divided by the radius of the orbit. Okay, so let's do some cancellation. The little m's cancel out, which means that the acceleration doesn't depend on the mass of this object. We can multiply both sides by r. And then we find that the velocity is equal to the square root of mg over r. In particular, the velocity of a distant planet is smaller than the velocity of a centrally located, the velocity of Neptune or Pluto is much smaller than the velocity, not just the angular frequency, but the actual velocity falls off as 1 over the square root of r. Now, if you look at galaxies through a telescope, what you see, of course, is light. And it was always believed that the amount of light coming from a region was proportional to the number of stars in that region and so forth. So it would be proportional to the amount of mass in that region. And galaxies are mostly cores, the center. And then there are these, some galaxies are spiral arm galaxies. If you look at them from the edge, they look like that. But most of the light and most of the material, the observable material, the light matter means the matter that you can see because it glows, because it gives off light. Most of it is in the core of the galaxy. So if you were to just take literally that mass follows light, that the mass distribution is comparable to the light distribution, and look at stars at different distances out here, they would mostly be moving in the field of a central object similar to the center of a solar system. If that were the case, Now we can also look down on this from above. It's a core, a very diffuse bunch of stuff out here that doesn't have much light coming out of it, and everything moves around. All right, we can measure the velocity of stars in such galaxies, or we can measure the relative velocity. We can measure the overall velocity of the receding galaxy. These are relatively nearby galaxies. We measure the overall recessional velocity, and then we measure the difference between the velocity of this point and that point. We discover that this point is moving toward us, this point is moving away from us, and in that way compare it with the overall velocity. We can pretty well calculate the velocity of orbiting, the orbital velocity, not calculate, measure the orbital velocity of stars as a function of the distance from the center. And what do we find? Not me, but what do the people who do this kind of work find? They find that the velocity does not fall off like 1 over the square root of r. Instead, it's pretty constant. The velocity of, not the angular velocity, it takes longer to go around far away, but that's because it's a longer distance. But the velocity of a star over here is about the same as the velocity of a star over here, is about the same as the velocity of a star near the outer edge of the galaxy. So there's something wrong with this picture of the galaxy, that it's mostly composed of matter near the center. All right, so you can do something else and say, wait a minute now, let's see if we can figure out where the matter really is. Maybe mass doesn't follow light. Maybe the light distribution is not a good sampling of the mass. So let's use what we do know about these velocities to see what we can say about how the mass is distributed. Okay, now think of, let's suppose now that the mass is not concentrated at the center, but it's distributed in some way. It's distributed in some way, and for simplicity, let's say it's distributed nice and symmetrically. Then what mass should we be using in here? For a planet, or not a planet, for a star at distance r from the center. What mass should we be using in here? Well, we should be using all of the mass out to a distance r. Remember, a planet or a star moving at a certain radius feels all the mass inside that shell. So we can correct this formula, and we can say, let's correct this formula and say the right formula is m of r times g, m of r times g. The meaning of this m of r is it's the amount of mass in a sphere of radius r. So far, we've not assumed anything particular about that distribution of mass. We've just assumed that there's a notion, a functional notion, of the mass within a sphere of radius r. This formula is very general. Of course, it also doesn't say anything. You don't know what m of r is, but you measure v. But v, you discover, is constant. You discover that all of these velocities are the same. So what does that say about m of r? It grows linearly with r. The amount of mass out to distance r is proportional to r. So the amount of mass in a sphere of radius r apparently grows like r. What about the density of mass? Does that grow? No, we have to divide by r cubed if we want the average density of mass. The average density of mass, we would want to divide by r cubed. And no, it doesn't mean that the density, that it gets denser and denser as you go out. But it does mean that there's a halo of mass out there which is more pronounced, that most of the mass of the galaxy is out far out near the edges and maybe even beyond the visible galaxy. Right? Now you say, okay, we can use the velocity to actually tell us what m of r is. We can figure out, using the velocities, we can tell what the mass out to a given distance r is, and we can compare it. Take the whole galaxy out to its very extremities. We know what the mass distribution is just from these, from the rotational speed of the stars, and we can say how much mass is there altogether. How much mass is there in this hidden unobserved mass? In the hidden unobserved mass that does not follow light, it is not proportional to the light, there's about 10 times the mass that we would normally associate with stars and luminous objects that produce the light of the galaxy. In other words, the estimate of just saying that the galaxy is made up of stars or luminous matter like stars captures only about 1/10 of the mass of the galaxy. The galaxy is at least 10 times heavier. Yeah.
That's only counting the dark matter in the stars.
That's correct.
So there could still be more dark matter.
Yeah. I think that that's true. That is true. I may be. I think what's true is the total mass that's expected to be in a galaxy is about 10 times the mass of the luminous matter. It does, of course, fall off when you go far enough away. But you're right. Out to the boundaries, it follows this dark matter curve, and I believe the total mass of a galaxy is roughly about 10 times what you see with light. Let's see, is that right? I think that's approximately right.
90%.
Yeah. What? No, dark energy is about 30%. Dark energy.
Ordinary matter is 4%, dark
Yeah.
matter is 30 or 40.
So it's about 10 to 1.
10 to 1, 10 to 1 is about right.
Right. Dark matter, right. Luminous matter is what, about 4% of the whole? And the dark matter is probably another 30%. So it's something like a factor of 10 or 7 or something like that. 4 times 7 is 28, yeah.
But for some galaxies, there's evidence that a lot of the dark matter is beyond the last luminous
Yeah,
star.
yeah. But I think the total amount of it is about 10 times the mass of the galaxy. Total amount. But some of it extends out beyond the galaxies. I'm not an expert at this, incidentally, but
How the density, it looks like the density sort of go 1 over r squared.
well, yeah, you
Do they
can.
have a reason for
Let's see. No, but I don't. This is not something that's subject to anything except simulations, and simulations account for some of it, but I don't know how
Are
much.
these ratios true for all galaxies and galaxy-like structures?
Say it
Or is there
again?
variation, like some galaxies?
Yeah, I think for all big galaxies, yeah. Yeah, it's pretty much the same. We can calculate what the density is. Let's see, the density is such. You have rho, which is the density. Let's do it a little bit better. Rho of r. Now, if you integrate rho of r, now what do we have to integrate it with to find the mass within a shell? 4 pi r squared. In particular, r squared dr, right? And you're right, 4 pi, but I don't care about the 4 pi. This is the thing which is equal to 1, you integrate it from 0 to capital R, and this is the total matter, the total mass within radius r, and this is the thing which grows as r. Okay. So, how would you solve this equation? Well, we can differentiate both sides of it with respect to r. What happens when we differentiate an integral with respect to r? You just get the integrand, right? So we get rho of r squared is equal to 1. Rho of r looks like 1 over r squared. Rho of r is 1 over r squared. All right. But there's a lot of matter out there, and about 10 times what's in the galaxies. What do we know about it? It doesn't shine. So that's one thing. It doesn't produce light. Another thing we know about it is it didn't contract. It's much bigger halo than the size of the galaxy. The galaxy is a fairly small thing embedded in a big halo of this dark matter. The dark matter is in a form of a spherical halo, even if the galaxy is in the form of a disk galaxy of some sort. At least that's expected, and it's, I think, even observed. So it's a big globular blob of mass that has not contracted together with the luminous matter to form a smaller, more concentrated thing. What is it that causes the contraction of a bunch of gas to a smaller? Lower the temperature? No. It shrinks. When it shrinks, the temperature goes up. That's why stars form. When it shrinks, it goes up. It's a friction, dissipation of some sort or another. Some form of dissipation, some sort of collisions, some sort of friction is the thing which causes. If you just started with a ball of gas, and the gas is going back and forth, oscillating, some of it's going around in a circle, nothing much happens to it. It just stays about that size. It shrinks because of collisions and because of radiation. It radiates away energy, it shrinks. Interesting kinds of collisions and processes have to happen in order to cause it to shrink. Well, ordinary matter has plenty of different kinds of processes. In particular, it radiates light. And the radiation of light causes it to collapse. And other kinds of processes, collisions between atoms and so forth. Whatever this stuff is out there, it's very collisionless. And it doesn't radiate light. So it's very weakly interacting somehow. It doesn't do very much other than gravitate.
Wouldn't that make it unstable? It'd be unstable structure?
No.
Because gravity would force it to collapse. What keeps it out there?
Kinetic energy. Okay, what keeps the Earth going around the sun? Why doesn't the Earth fall into the sun?
Because there's no friction.
No friction. Right, but there's a little bit of friction, so the Earth is slowly falling into the sun. And at one time there was more friction, which caused the primordial gas cloud to coalesce and condense into things. So whatever this stuff is out there, it has a lot less friction than other matter. Yeah.
Is this a torus at a distance, or is it
Is it what?
a spherical shell?
No, it's not a shell. It's a sphere, but whose density goes down like 1 over r squared.
So it's a sphere, it's not a torus.
It's a sphere. No, not a torus. Not a torus. Torus would be very hard to. No, it's not a torus. It's a sphere. Large spherical blob. Yeah.
Question comes up. Possibility of intergalactic dark matter or dark galaxies?
Dark galaxies. You mean just a blob of dark matter?
Yeah, I mean, it would gravitate, so.
Yeah. Yeah.
How do you know it's not neutrinos?
Neutrinos just wouldn't behave that way. They're moving too fast. They're moving too fast. They have to
These
be
are very
slower.
slow particles.
Hmm?
These are slow.
These are slow. These are
Is it
slow.
correct to call it a sphere, or is it a ball?
A ball. Well, it's not a uniform ball. It's a ball. Yeah. Yeah. a ball which is more dense in the center, but the density doesn't suddenly fall off like the light does. It gradually falls off.
Follow-up question.
One at a time, just a minute.
How do we know that there's dark matter outside the luminous stars you see going around? In other words, you can measure the velocity of the different arms of the galaxy and say how much matter's inside that. I don't know.
But you can, yeah, you can tell, you can roughly estimate the mass of a galaxy by looking at the motion of other galaxies in the vicinity of the galaxy. So, what's that? Well, colliding galaxies, but just the motion of I don't know, I suppose the motion of the Magellanic Clouds and things like that to tell you something about the total mass it must be the motion, the relative motion of nearby galaxies, which give you some hint at what the total mass of the galaxy is.
A black hole would not be counted as dark matter, is that true?
No. Dark matter is very definitely collapsed. You mean, could it be a bunch of black holes? People have talked about that, and I think the general conclusion is no. But I'm not really sure exactly why.
There would be
I know
lensing.
enough.
Wouldn't there be lensing if a massive thing passed?
There'd be lensing. But also, if those black holes originated from ordinary matter, it would say that in the primordial universe, before those black holes formed, there was a lot more ordinary matter out there. And that would be deadly for nucleosynthesis and the origin of the elements. So the best bet, I think the best bet by far is just that they're elementary particles which are very weakly interacting.
Galaxies seem to have net angular velocity.
Oh, absolutely. But they're not as flat, or they're not, the dark matter is not as flattened as the galactic plane would indicate.
But presumably they have the same net angular velocity.
Not necessarily.
Not necessarily.
No, I don't think so. I don't think that's...
And where does the angular velocity come from of the...
Well, I mean, you know, the angular velocity of the solar system is not the same as the angular velocity of the sun. In fact, the angular velocity of the solar system is not exactly well defined.
Is not what?
Not exactly. Yeah, good. Yeah, I would say that the angular... I don't know what's known about the rotational motion of the halo. I don't know.
The dark matter halo.
The dark matter halo. That's a good question.
It would be hard to tell anything about it at all,
Yeah,
really.
I don't know the answer whether anything is known about the rotational motion of the halo.
Decreasing energy?
What's that?
Is the dark matter decreasing energy?
Decreasing energy in what sense?
In the dark matter, the energy is decreasing
Decreasing with respect to what? Time?
as a function of time.
Why would it be decreasing? It's pretty much staying the same. It's not changing very much. It doesn't interact with anything. Yeah, it doesn't lose kinetic energy very
What about
easily.
dark energy? How does that...
We haven't, that's another question. We haven't come to that. We can...
When you're estimating the ordinary matter in a galaxy, if you add up all the planets and the Oort cloud and the Kuiper belt and all that stuff in a solar system, how big a fraction of that is of the total mass of a solar system?
I think it's pretty small.
Yeah.
Very small. The
Small
solar
compared to
system
the
is
sun.
mostly the sun.
Yeah.
From the point of view of conservation of angular momentum from the Big Bang, it seems like if there wasn't any net angular momentum of that initial mass and you have different galaxies, they would net out to not have a greater angular momentum. So does that come into play with also the net angular momentum of
Are you
purported,
asking whether the angular momenta of galaxies show some alignment? Is that what you're asking?
well, I mean, they all couldn't be spinning clockwise from at one
They
direction.
sure aren't. So, I would have been,
That would-
somebody
that
would
would-
have noticed.
Right. But from that point of view, can you conclude anything about the angular momentum of these dark matter clouds, that they would also have to balance to?
I don't think, well, I think you probably, I think it's pretty darn certain that they average out on the average, but whether the angular velocity of, I think the question was, is there some locking which locks the visible galaxy to the halo? I think that was the question. I don't know.
Presumably the
I will try to find out. I don't know.
Presumably the angular velocity of the galaxy came from something that happened.
You would think that at
in
least
the
they,
early
you
universe,
think at least they
and
probably
maybe
point in the
things
same direction, the angular
would
velocity.
spin up the.
Yeah. But even that I don't know, and I don't know if it's measured. It's a good question. I really don't know the answer.
We don't know if it's dependent, the dark matter.
What's that?
The dark matter shell is dependent on the light matter torque.
Well, it seems like the dark matter is more the primordial thing that coalesced. It was probably the first thing to start coalescing into well-defined structures, and the ordinary matter probably followed it, got trapped by it, but then the friction of the ordinary matter and collisions caused it to sort of continue to shrink, while the dark matter, being largely transparent to itself, didn't shrink, except the only thing that affects the dark matter is gravity. Gravity is enough to cause it to condense and start to shrink and start
So its
to...
only common denominator is a gravity.
What's that?
Its only common denominator between the light.
Yeah. Yeah, that's the only serious interaction between them.
Well, then where did all the kinetic energy come from that's keeping it from collapsing if it doesn't interact? Except for gravity. You said kinetic energy is keeping it from collapsing. Where did that energy come from?
From potential energy. It originally started with a pretty uniform distribution, but don't think of it as uniform distribution. Just think of it as very large, diffuse blobs of gas. Very, very large and very diffuse. And gravity pulled them together. Gravity caused them to contract. And they contracted some, and in the process of contracting, potential energy got converted to
Is it the case, I just had a question here about the mechanics. Is it the case if you have particles that don't interact except gravitationally, and they're in a disk, it's unstable and it must evolve to
I suspect the disk is unstable.
So it has to evolve to a radially varying, but other than that,
Yeah. Now, how the globular structure manages to stabilize the disk-like structure in it, that I don't know.
Maybe related to polarity?
To what?
Is it the polarity, uniform polarity within the galaxy or something?
What does a polarity mean?
Magnetic polarity.
Oh, it doesn't have to do with magnetic fields. It doesn't have to do with magnetic fields. I don't think so. Even that I don't know for sure. This is really the subject of people who do large-scale simulations.
There's just less friction in the disk than there is in more random orbits. Because if they're rotating a disk, they run into each other much less often than they do if all the orbits are going
wildly haywire.
Every which way.
Yeah, I'm sure that's true.
So it would seem to be that at least there's some chance that a dissipative process would lead to a disk-like structure.
No, it certainly did in the solar system.
And around Saturn and.
So I don't know. I'm beyond my pay grade now. I'm not enough of a gastrophysicist to know the answer to these questions. Yeah.
How do they get an estimate for the amount of dark matter between the galaxies?
Well, I think from the relative motion of galaxies. The relative motion of the galaxies themselves is sensitive to the material between them. And,
Is there much dark matter? I thought that most of the dark matter was right around the galaxies. There wasn't much of it.
well, it's spread out something like this. And how far that goes out, does it continue like that until you get to the next galaxy, sort of, or does it tail off and then a flat region in between? I don't know the answer. Let's see. A galaxy is, how big is the galaxy? 100,000 light years, right? Something like 100,000 light years. And the distance to the next galaxy is about 1 million light years. 2 million light years, something like that. So,
everything I've seen, basically the dark matter within the clusters of galaxies has no uniform distribution. It's like clouds in the sky. There's more dense and less dense regions.
Yeah.
And it's kind of
associated.
disturbed by the progression of the galaxy, the motion of the galaxies within the cluster.
the point being what?
Well, they mapped out
Yeah, dark matter.
the density, the relative density of the dark matter
Right.
within the clusters, and they show these clouds of stuff
Super
that's kind of
clouds.
random in nature, which says that the galaxies collect it, and it goes by
Right.
the 1/r², but that either increases or decreases when they pass through each other.
Oh, that's for sure. But you know how it's distributed in the region, halfway between the galaxies, I don't know.
Yeah, getting back to the single galaxy model that you have up there, in most galaxies have a supermassive black hole or black hole.
But that's a
within
very
the
small
galaxy.
fraction of the mass of the core.
Is there any way we can analyze dark matter in that perspective in terms of the black hole?
I think the dark matter is rather is so diffuse and spread out over such a large distance that I don't think black hole is a tiny little thing at the core, so I don't think so. There's a
microscale, is there any interesting measurements within the solar system using planetary motion to set any kind of limit?
on dark matter? Well, there are limits. There are various kinds of limits on the nature of the particles, which might be the dark matter particles.
But I mean, just by looking at the motion of the, I don't know how accurately measuring the motion of the planets, but we can see general relativity, but I wonder if you can see dark.
You mean, is the dark matter appreciably affecting the gravity of the solar system? I don't think so. No.
What sort of experiments are they, I mean, if they don't interact except for gravity, what sort of experiments are they putting up to try to detect these
Well,
particles?
when you say they don't interact, I mean...
or maybe they just interact very weakly, you mean?
Yeah, I mean, if an electron passes through a lump of lead, it will interact with a lump of lead every single time. If a dark matter particle passes through a lump of lead, it may interact with the lump of lead 1 out of 10 to the 13th times or something. Well, you just let 10 to the 13th dark matter particles pass through and you'll discover one of them. So you just use the statistics of large numbers. And there are lots of detection schemes that are out in place there searching for dark matter. Thus far, they're always out of the range of detectability.
Wouldn't there be a signature of dark matter in falling towards the black hole, event horizon?
Well, it's too diffuse. It's very diffuse.
Is there any reason to believe that the dark matter is essentially in circular orbits? I mean, again, you'd have to get to some dissipated.
I don't think there's any reason to believe it's in circular orbits. Probably not in circular orbits. I don't think there's any reason to believe.
So there could be some very, very highly elliptical orbits.
Yeah, there's probably things like that.
So
Some
of the dark matter could, in fact, just by accident, run into
Sure.
the black hole of the
Sure.
center.
Sure, but it's very diffuse. I mean,
And extremely elliptic orbits are eliminated by the black hole at the center.
But the black hole is a tiny, tiny, tiny little geometric object at the center of the galaxy. So you're eliminating a very, very little bit that way. Yeah, no, I think there's no reason to believe that the orbits are circular. The orbits are probably all over the place. Some circular, some elliptical, some very elongated. Some of them just going back and forth, except not hitting the.
And they'd be deflected by a neutron star and every other mass as well.
Deflected by everything, yeah.
It's all stirred up.
They'll pass through the planets and the stars, and presumably.
They presume, yeah, they pass through most things. Yeah, I don't know if they pass through a neutron star, but they probably pass through the Earth very easily, right?
If you had some sort of statistical probability distribution on the types of orbits, then you could probably get the rho of r as 1 over r squared, maybe? Or divide what the rho of r would be?
No, I don't think there's any easy way to get the 1 over r squared. I don't believe there is. For that, that's equivalent to knowledge of the distribution of energies, and it doesn't fit anything simple. It's not a Boltzmann distribution. So I don't think there's any simple way. As far as I know, it is not known exactly why the distribution is what it is. Now, there's lots and lots and lots of simulations, and I don't know what the state of the art is.
With gravitational lensing, if it was diffuse, you could try and measure it that way. If it's a significant portion of the mass, you'd have like twice the lensing effect, wouldn't you? By trying to like image, galaxies behind it or around it or something like that.
Oh yeah, you can. Yes, the lensing due to galaxies is sensitive to the. Is that what you're saying? It's sensitive to the mass. Absolutely.
You'd have like a relative effect if you took a look at the optical mass or radiation, and then it would be significantly larger.
Yeah, so dark matter causes lensing. Right.
It does?
Oh yeah. Dark matter is part of the mass which causes lensing. So it's.
Is there something to suggest in observation that by way of lensing you can discern the distribution of dark energy?
I'm sure there is, but I'm not an expert at it. But I'm sure there is. I mean, that's a very obvious thing to try to do, is to map out the dark matter by lensing.
There was an article where they looked at galaxies that were colliding, and because the visible matter interacts with those stars, populations of stars interact, you get basically two hypotheses about how the lensing, and the evidence seems to be that there's I guess a different lensing effect, because the dark matter doesn't interact in the same way. And
Are you talking about the bullet galaxy?
Yeah, the bullet cluster is a pair of galactic clusters that are interacting.
Yeah, right.
The gas on
That's
the
right.
inside, which is regular matter, is hot and is seen in X-rays. And then you can measure the distribution of the total matter by looking at gravitational lensing. So you get a distribution of total matter and a distribution of normal matter, and what's left over is assumed to be dark matter.
The point is that when the two galaxies collided, the ordinary material interacted in a significant way. The dark matter clouds just interacted gravitationally and was not such a significant interaction. And the result was a separation of dark matter from the other matter. And so there's an example. The controversy had to do with whether there really was dark matter or whether Newton's or Einstein's gravitational theory had to be modified. You could try to fit the rotation curves of galaxies by modifying Newton's force law. We got it from Newton's force law. Where is it? Over here. By modifying Newton's force law, and in that picture there really wouldn't be dark matter. or the gravitating effect would be modified, but it would still be attached to the same masses. It would be quite clear that that would not be a good description if it was possible to separate dark matter from the ordinary matter. Okay. And apparently in these bullet clusters, this is bullet cluster, two galaxies collided, and the effect was a separation of the dark matter from the luminous matter. And so that kind of settled the controversy of whether there is dark matter or whether it's simply a modification of Newton's law.
Is the luminous matter only referred to the visible spectrum?
No. No, any way that you can see it. Any way that you can see it optically, any way that you can see it electromagnetically. But yeah, I think in first approximation, yes, it was the visible light. The visible light, for the most part.
Well, certainly they use radio telescopes to look at the same objects.
Yeah. Yeah. You are right. Right. But the original hypothesis was that that mass followed light, that the luminosity was a good measure of the abundance of mass.
So, but that matter may emit in a different field, different region of the electromagnetic spectrum.
Well, I think we would have noticed if it emitted any appreciable amount of radiation into other, now, it's possible that dark matter, for example, annihilates and creates gamma rays. Right. Sure. Sure. But that you wouldn't see through ordinary telescopes. You see it in particle detectors. And, yeah. Right. Good. Okay.
So there must be a continuity between dark matter and visible matter.
Continuity.
Kind of.
Well, they seem to be two very different things. They don't seem to be, very little is known. What I would say about dark matter is very little is known in detail about what it is, but it's entirely consistent. It doesn't require any radical modifications of the rules. That there are more particles than have yet been discovered, I think we all believe. We've probably just touched the surface of all of the particles that exist, and that there are particles which can be very weakly interacting. We already know there are neutrinos, as was mentioned. And so without doing any radical damage to any of the principles of physics, we can easily accommodate dark matter by just saying it's particles that we haven't discovered yet. Well, it sounds funny, but it's probably what it is. It's probably what it is. It gives every indication of not being anything radically different. And since everybody and his brother has postulated a particle for one reason or another, and often for very, very good reasons, there are probably more particles, many of them weakly interacting, and that's probably what they are. If not, but...
Wasn't there a thought that there's a lot of hydrogen you can't see, unionized hydrogen that kind of made up this mass? It seems to me that was a...
There was a time when people thought that it might be just hydrogen. There was a time. Nobody thinks that anymore. And I think at least one of the reasons is because the amount of it is so large that it would have radically affected the creation of helium in the early universe, and radically affected the nuclear physics of the first 3 minutes in some really awkward way. So there's just too much of it to fit into any... when we talk about nucleosynthesis, we'll talk about that a little bit. There's too much of it.
And is there or not any evidence that dark matter has either electrical or magnetic properties?
Well, the evidence is it doesn't have very much. They're not, they're probably neutral. They certainly don't have any significant electric charge.
The standard model has no, doesn't talk to any possible
Standard
properties.
model does not have particles of this type. The supersymmetric standard model has 1,000 of them, I mean, you know, all over the place, and so sometimes people regard this as evidence or weak evidence of supersymmetry. That's a bit of a stretch, but it could be. But there's a lot of good reasons, you know, really sensible reasons for thinking that there are more particles. And so the dark matter could be any one of them. It could be a combination of them. I think we'll find out. I think that's not out of the question to find out in the next 10 years.